So now we look at an introduction to alternating current and voltage. So we're going to shift gears here a little bit. You're going to see a lot of trigonometric relationships and trigonometry related calculations as we move forward into AC and alternating voltage. We're going to look at how do we break down a sinusoidal wave, the sinusoidal voltage and current values, angular measurement of a sine wave, and the sine wave formula. So in doing this, we're going to look at the characteristics of the sine wave, determine various voltage and current values, whether they're instantaneous, or if they're values that we use calculating vectors, or what we call phasors. Describe the angular relationships of the sine waves, and then do the mathematical analysis, and then start to use the phasor representation. So we've got a lot of new terms here that you need to become familiar with. Again, just like I tell you with all of the other things, you should be copying this information down, these new terms down into your notebook that you keep handy as you're going through the material, so that as you encounter a new term or a new relationship, you can get to it quickly without having to dig through your textbook to try to find it again. So the sinusoidal waveform or sine wave is a fundamental type of alternating current AC and alternating voltage. When we say AC, we're referring to alternating current, but we know that we're talking about both the voltage and the current, and you're going to see that as we move forward. It's also referred to as a sinusoidal wave, or simply a sinusoid. The electrical service provided by the power company is in the form of a sinusoidal voltage and current. In addition, other types of repetitive waveforms are composites of many individual sine waves, and we call those harmonics. And we will learn as we go along how you can dissect the harmonics and determine what the fundamental and each of the individual harmonics are and look like. So sinusoidal voltages are produced by two types of sources: rotating electrical machines, AC generators, or electronic oscillator circuits, which are used in instruments commonly known as electronic signal generators, something that you will encounter in your labs. When you do your lab works, you're going to encounter those electronic devices that create AC signals. AC generators are covered later in this section. The graph shown in 11.2 below is a graph showing the general shape of a sine wave, which can be either an alternating current or voltage. Voltage or current is displayed on the vertical axis, and time is displayed on the horizontal axis. So you get your amplitude on the up-down, the y-axis, the vertical axis, and then along the timeline. Since we are in time domain, later we're going to find out there's something called frequency domain, and things look differently in the frequency domain. But you can see here we start off at the origin at 0 volts. We go to some maximum positive voltage or current. We go back through 0 volts. We go through some negative maximum current or voltage, and then we go back to the 0 point. And if it is something that is continuous, you will see this occur over and over again, and we will determine something called the periodicity of a sine wave. Over here on the right, you can see we have a symbol that you'll start seeing in your diagrams for the sinusoidal voltage source. As mentioned, the sine wave changes polarity at its 0 value. That is, it alternates between positive and negative values. When a sinusoidal voltage source V sub S is applied to a resistive circuit, as in the figure below, an alternating sinusoid current results. When the voltage changes polarity, the current correspondingly changes direction, as indicated. So you can see here we've got a simple circuit here with a load with a resistor on it. We apply a sinusoidal voltage to it. When the current moves in one direction, you can see we have what's called a positive alternation. When the current moves in the opposite direction here, you can see we have a negative alternation. The combined positive and negative alternations then make up what we call one cycle. So one cycle is from, in this case, 0 to 0, where it starts over again. So we need to define something called the period, or the periodicity of a sine wave. A sine wave varies with time in a definable manner. We can look at one period or one cycle from 0 to 0, or we can look at it as it occurs over and over and over again, as depicted here in 3 cycles. So the time required for a sine wave to complete one full cycle is called its period. Typically, a sine wave continues to repeat itself in identical cycles. Since all cycles are repetitive and repeat the same sine wave, the period is always the fixed value for a given sine wave. The period of a sine wave is measured then from a 0 crossing to the next corresponding 0 crossing, as indicated. The period can also be measured from any peak in a given cycle to the corresponding peak of the next cycle. So if we start here at 0 and go to 0 here, we've covered the period. If we move to the other diagram, we go from this peak to this peak, we've covered the same amount of time. That's considered one cycle. We can do the same thing here on the negative part, from this peak to this peak. So you just pick your reference and measure accordingly. Sometimes it's easier to measure at the peak. Sometimes it's easier to measure at the 0 crossing. So in this example, what's the period then of the sine wave shown here? Well, you can see we've got some maximum voltage, we've got some time indicated, and we have hash marks for every period of the wave. We have 0 to 4, 4 to 8, 8 to 12. So as shown in the figure, it takes 4 seconds to complete each cycle. First 4 seconds, second 4 seconds, third 4 seconds. Therefore, for this waveform, the period is 4 seconds. Okay? Let's move over here. Show 3 possible ways to measure the period of a sine wave. How many cycles are shown? So method 1 says the period can be measured from the 0 crossing to the corresponding 0 crossing in the next cycle. The slope must be the same in the corresponding crossing. So basically it's just telling you that this first one and this second one have to look exactly the same. Okay, the slope there is the same. The second method then, the period can be assumed from a positive peak in one cycle to the positive peak of the next cycle. So from right here to right here. Correspondingly true, we can do the same thing with the negative peak. So the negative peak here to the negative peak here will measure the period. So again, you pick one. Sometimes when you're doing this on an O-scope, sometimes it's easier to see if you measure at the peaks, negative or positive. Sometimes it's easier to see where it crosses the 0. So these measurements then are indicated where 2 cycles of the same sine wave are shown. So you can see here they're giving us some measures and some terms. Here we have 0 to 0. Here we have time from peak to peak. Here we have it labeled as peak to peak. Here on the negative side, time peak to peak, or time 0 to 0. So whichever is the most convenient for you to do your measures is the best way to do it. So the frequency of a sine wave. The frequency of the sine wave is the number of cycles that a sine wave completes in 1 second. So you can see we're tied to time. We're tied to per unit of time. So frequency is basically 1 over time. What does that make time? 1 over frequency. We're going to see that. The more cycles completed in 1 second, the higher the frequency. Frequency, we usually use a little f, is measured now in units that we call the hertz. Way back when, we called it CPS, or cycles per second. Now the standard is to say hertz. So 1 hertz is equivalent to 1 cycle per second. 60 hertz is 60 cycles per second, and so forth. And there are lots of variations of sources that provide different frequencies. So we can see in the diagrams below, we've got one that's a little stretched out here, one that's a little compressed. The one that's more compressed, of course, is at a higher frequency than the one that is more elongated. So they show us here the the duration of 1 second to complete 2 seconds, or 2 cycles. In the next one, you can see we complete 1, 2, 3, 4 cycles in 1 second. Okay, so in part 1, B completes 4 cycles a second, where in the other one we get 2 cycles per second. So as I said, what's the relationship between frequency and period? Well, if we define frequency as a per unit of time or a per second relationship, 1 over t, then the corresponding inverse or reciprocal is time is equal to 1 over frequency, or 1 over f. So there's a reciprocal relationship between frequency and time. Knowing one, you can calculate the other. The easiest way to do that, again, you pull out your calculator, you look for this key along the top here. In this one on the Casio, it's right over here. It's the x to the minus 1. Some calculators have a 1 over x. My old Hewlett-Packard here, if you look here on this one, you can see it says, maybe you can't, but that's the key right there, 1 over x. This inverse relationship then makes sense because a sine wave with a longer period goes through fewer cycles in 1 second than one with a shorter period. So let's look at an example here. Which sine wave has a higher frequency? Determine the frequency and the period of both sine waves. So in this case, you can see the graph is showing us here 1 second. We have 1, 2, 3 cycles. In B, we have 1, 2, 3, 4, 5 cycles. Okay, so this one actually is going to be a higher frequency. So the sine wave in figure B has a higher frequency because it completes more cycles in 1 second than does the sine wave in A. So 3 cycles then are completed in 1 second, so the frequency is 3 hertz. 1 cycle then takes 0.333 or 1/3 of a second, so the period is 0.333 seconds, the inverse of 3 hertz. In B, the frequency is 5. The inverse of 5 then is 2/10. So 0.2, 1/5 of a second, is a period of 2 milliseconds. So the period of a certain sine wave is 10 milliseconds. What's the frequency? Again, we put it into our relationship. Frequency is equal to 1 over time, which is 1 over 10 milliseconds, which is 10 times 10 to the minus third when we convert milli back to an exponential. And we can pull that into the numerator. We get 10 to the third then, okay? And when we pull 10 into the numerator, that reduces it by 1. We get 100 hertz. The frequency of a sine wave of 60 hertz then has 1 period. So time is equal to 1 over frequency. 1 over hertz gives us 16.6 milliseconds. Again, you just put 60 in your calculator, hit the x to the minus 1 key over here on the calculator, and boom, you get 16.7 milliseconds of time or period. Okay, so when we come back, we'll take a look at electronic signal generators and how these guys create the signals that we're looking for these types of measurements.